Alright, hi there. This is our first topic for this course in ABE164, and in this week topic we'll be discussing the fundamentals of electric circuit theory. Now, the study of static and moving charges is actually under the umbrella of electromagnetic field theory. However, because of its complexities, then a simplified version is necessary and it is convenient, and of course it is based on some assumptions, and in that simplified version, that's what we call the electric circuit theory. So we're not going to discuss the assumptions for now, but I just want to give you a picture or a bigger picture of all this. That's what all that we are going to discuss on this point onwards, right? So that's under the electric field electric circuit theory. Okay, now in the study of electric circuits, of course there are basic electrical quantities that we need to discuss. So just like in the study of mechanics or in thermodynamics, we discussed the let's say the mass, the velocity, or in thermodynamics the heat, the temperature, and all that. So the same is true in the study of electric circuit, right? So we have here three basic quantities. We have the charge, the current, and the voltage. Now when we say charge, it is an electrical property of the atomic particles of which matter consists. So that means that that a matter actually it has a charge. Okay, so just like in mechanics, any matter it has a mass. So it is a property. But in electric circuits or in electrical phenomena, we have here charge. So that means that if here's our electric circuit, a simple electric circuit right here, and if we try to zoom this in, what we see, is, of course, you can see the insulation of the wires, and also we can see the strands of the wire if it is a stranded wires, right? And if we zoom that some more, then what we see, or we will arrive into atoms, right? So let's say we have atoms, we have this nucleus, and we have these protons, and we have these electrons and these orbits. Okay, so that's what we have learned in basic chemistries, right? So we have protons and electrons, and those electrons and protons, they have charges. All right, so they're the ones exhibiting the charge. Okay, so one is negative, that's electrons. One is positive, that's for electrons. So protons and electrons, and the value of these charge is that's 1.602 times 10 to the negative 19. So Q, let's say for electron, that's negative because electrons have negative charge, right? And the unit is in coulombs, right? That's coulombs. Okay, so when a charge moves, or when there is a transfer of these electrons from one orbit to another, or to another atoms, then that flow of charges is what we call the current, right? So if let's say here's our wire once again, right? So let's say here's our wire, and here's our copper wire inside. So we say that we have these electron charges, let's say negative charge right here. So there's a lot of negative charges, and when this moves, let's say from point A to point B, so when that moves, so at this cross section, the rate of change of charge per unit time, okay, so the rate of change of charge per unit time, that's what we call current, or basically it's just simply the flow of charges, right? So right here we have negative charge, so it moves. So of course there's a lot of charges. Okay, and the unit of that is in amperes, or shortcut is letter A. Now, in order for this charge to move from one point to another, let's say from point A to B, in order for this charge to move, there must be some force, right? And to move a unit charge, when you say force, then somehow we can relate it to work, right? So that work done per unit charge is what we call the voltage, right? So V is equal to dW, that's the rate of change of work per unit charge, and the unit is in volts, or shortcut is letter V. Okay, so another quantity is the power and energy. So when I say power, it's the rate of doing work. So that's the work per unit time, or the energy per unit time. Okay, and the work done to move a unit charge is this one, right? So that's the W all over dq, or that's the derivative, and then the rate of change of charge per unit time, that's this dq all over dt, and that's just simply the amperes, and this one is simply the volts. And therefore, the rate of doing work for a charge is expressed in this formula. So P is equal to VI, and the unit is in watts. Right, so those are the basic quantities for electrical phenomena. Okay, so again, a charge, because simply there is, the existence of matter, there is a charge. And the movement of charge from one point to another is what we call the current. And in order for that charge to flow from one point to another, that's what we call the voltage, or we need something to do some work done. And the rate of doing work is what we call the power. Right, so energy, I think we'll not include this for now, because power is the rate of doing work, whereas energy is the basically defined as the capacity to do work. So rate is per unit time. Okay, so now let's talk about the circuit elements. So let's say circuit, it is a connection of various circuit elements in closed paths. When we say elements, it's something like the building blocks of a complex, of a bigger circuits. So what are those that comprises that bigger circuit? Or you can relate this in, let's say in structures, we have structural elements, right? So let's say a building. So a building has, or a building consists of various structural elements like the columns, the beams, the braces, the floors, and all that. So those are structural elements. And for machine elements, let's say machine elements, so a machine consists of, let's say we have pulleys, we have gears, we have chains, and many other elements, right? So those consist let's say the entire project, right? So let's say here's our gear. So in the same way, for electric circuits, then we also have circuit elements, right? So right here we have a simple, or probably the basic circuit elements. We just have the source, a voltage source. So right here we have a battery and a load, and we have these wires right here connecting so that it can have a closed path. Okay, so that's the fundamental requirement of a electric circuit. It says that connection of various circuit elements in closed paths. So this one provides the voltage required, and somehow it does produce power on these loads. Okay, so we have battery. We have this circuit diagrams. A battery, that's the symbols, and for a light bulb, let's say we use the symbols. Okay, so now let's move on to this classifications. So here's the circuit elements, and we can divide it, or we can classify it into active and passive. Right, so active means that it's the one giving the power to the electric circuit. So the power could be in terms of voltage or in terms of current, because we know the relationship P is equal to V I. And for passive elements, we have these three basic ones. We have the resistors, inductors, and capacitors, and they are something like the load elements. Okay, they consumes power. Okay, so now let's discuss this in detail. So resistors, right? So resistors, there we have the symbol right here. Right, so here's our symbol, and there are elements that resist the flow of currents. Okay, and because it resists the flow of currents, then somehow it dissipates energy in the form of heat. So let's say we have this wire. Once again, we have this load right here and a source, and because it's connected in a closed path, then there's current flowing. So somehow in that wire, I mean, when the charge, or when the flow of charge is passing through that wire, it actually experiences resistance, because the fact that there is a matter, there is a material wherein the charge has to flow, it has resistance. But in some analysis, that resistance of wire may be negligible. So sometimes in elementary calculations or basic calculations, we don't, or in short distances, we don't have this resistances, or we neglect the resistances of the wire. But for some applications, like for example, we have very long wires, then of course we need to include the voltage drop, because there is a resistance, so somehow there is going to be a voltage drop in that wire. And also, let's say in electric motors, even though there's a copper windings, there's a lot of materials in there, and somehow there's going to be some resistance. Okay, and also some devices are actually designed to have a certain resistance to control the flow of currents. So just like right here, we have these resistors, and we have some resistors that can be controlled. So I think the term here is potentiometer. So it's a knob, so you can actually vary the amount of resistance. Right, so those devices, or these devices, they're actually designed to have a certain resistance. It's easier to control the flow of current, so that, because sometimes we don't want that much current to enter in a circuit, for example. So we want to control that, so that we cannot, so that we will not burn our load, or our let's say our LED lights, or some circuits. Right, so we just want to control the amount of current, so we put resistors, these electronic devices, in those circuits. Right, so next one is inductors. Okay, inductors, they're we have the symbols, something like a coiled wire. So these are elements that stores energy in its magnetic field. The stored energy can be retrieved later. Okay, so it is a storage of energy, except that I think it's the kinetic energy rather than the potential energy of the charge. So the movement of the charge, it wants to resist any change of current. Okay, so something like the moment of inertia, I think, in the study of mechanics. Okay, so the basic principle is that a current passing through a wire creates magnetic field. So again, if we have this circuit, a closed, I mean, we have the source and we have this load, and it's connected in a closed path, then there's going to be current flowing. So when the current flows through a wire, it actually creates a magnetic field right here. So it's right here. So there's going to be magnetic field, and that magnetic field will grow, of course. At start, when there is no current flowing through the wire, then it has no magnetic field. But once it passed through, then there's going to be a building up of this magnetic field. So it will grow and eventually grow and reach its maximum capacity, right? So um, some devices are actually designed by coiling a wire around the core to increase the magnetic field. Like, for example, we have this wire and we coil that, and somehow that increases the magnetic field, right? So once that electric sorry once that magnetic field um, is built up, then somehow it wants to the flow of charge, it pres- it tries to maintain any changes in terms of its kinetic energy. Right, so something like the moment, sorry, not moment of inertia, but rather the mass moment of inertia. Right, so it's not the area moment of inertia, but rather the mass moment of inertia. So it resists the change in motion. It wants to, like here, let me try to explain. So let's say we have a ball right here and it's rolling in this direction. Then if once it rolls, then somehow the inertia tries to resist any stopping, right? So it wants to continue its rotation, but of course it will eventually stop. But the opposition to change in rotation is just at an instant, right? So at an instant of time, because eventually it will die down. Eventually the ball will stop. So just like here, the charges are the ones rolling right here, and once we have this magnetic field built up, then it doesn't want that. I mean, it's trying to resist any change in the flow of current. Okay, so take note, at an instant of time, of course. Now we use this circuit element for let's say to filter signals in some devices, like for example in electric motors we have windings inside, and also in transformers, let's say step down transformer to lower the voltage output, or maybe the current. So those are transformers, and also we have some relays. Right, so we have here an example. We have of a circuit. Let's say we have a source, we have this inductors, and we have this load right here, and we have this switch. Right, so of course when the switch is off, then there is no magnetic field yet right here. But once the switch is on, so once I turn on the switch, then there's gonna be a current going here, right here, and also a current going to this light bulb, and somehow there's gonna be a build-up in this electromagnetic field. Now when I try to turn this off, so when I turn this off, then there's no more power source. Then this inductor right here, because it doesn't want any change in the current, then even though this is off, at some point of time or at some interval of time, there's still gonna be current flowing through right here. Okay, and somehow produces somehow this light bulb still produces some light, right, at some interval of time. Okay, so that's that's why it's called the storage of energy. It stores energy in a magnetic field. But take note that storage of energy is it's actually something like the kinetic energy. Okay, next one is capacitors. So capacitors, we have the symbols right here. They are elements that stores energy in an electric field. So take note. So it's something like the the twin brother of the inductor, because if inductor stores energy in a magnetic field, but this one also stores energy but in an electric field, right? So how does it do that? It's simply because, let's say we have this wire right here. So we have a wire, right? So here's our wire, and here's another wire or a conductor, and it's separated by some dielectric material. So dielectric material. So because it's dielectric materials, then that means it doesn't pass any charges. I mean, it cannot pass the charge from this point to that point, right? So of course, electrons, we're just seeing electrons right here. So therefore, when there's a flow of current right here, then the electrons is going to build up on this side, right? So if this is going to build on this side, then the other sides would be positive. I mean entirely positive, because at start, when there is no current, and let's say this capacitor right here is not charged yet, then there's gonna be neutral. I mean, there's gonna be plus and minus on these plates, and then plus and minus on these plates. But once we introduce current to flow through this capacitor, then because this is a dielectric material, then it cannot allow the charges to pass, and so what's gonna happen is that there's gonna be some building. I mean, the charges, the negative ones, is going to build up on this side, right? So if it's going to build on this side, then the other side will have a positive charge. So once we have the positive and negative, then somehow we get this electric field, right? So it's a storage of energy, so something like a storage tanks in fluid systems. So it stores energy. So once we stop this flow of current, then this capacitor is already charged, and somehow it can produce some power. It can give that stored power at some time, right? So some devices are actually designed by to store energy in this way, right? So we can see this in electronic components. We have these something like cylindrical tanks, or these circular tanks, or no, not tanks, but electronic devices, right? So we can see that in the circuits, and sometimes we use this for pulse power because it's a storage device, and once it has obtained the required power, then sometimes we need that power at some instant of time, like for example in motor applications. So at first, in electric motors, when we're trying to start a load, of course it's gonna have some high torque, right? So at first it's very hard to start a load. I mean, relatively, of course, depending upon the application. So it's harder, but once it's already running, then it's no longer hard, right? So at that startup time, sometimes we need that additional power, and that's gonna be supplied by this. I mean, some types of motors. So we have these capacitors right here, right? And also in some gadgets, like for example in flashing of these cameras, then once we click this, right, to take a shot, then we need an amount of energy, and that energy will be coming from capacitors, right? And there's still many other applications for these capacitors, right? So in summary of these passive elements, we have right here, right? So here's our elements. We have resistors, inductors, and capacitors. Okay, so the symbol for resistor is R, and for inductor we use L, and for capacitors we use C. And the units for resistors, ohms, inductors, henries, and for capacitor, that's farads. And the symbol is this. So we have this Greek letter, I think, So that's the ohms, and the Henry is just letter H, and farads letter F. Right, so the property of these elements is what we call resistance, and this one inductance and capacitance. Take note, if we're referring to devices or elements, then that's resistors, inductors, capacitors. But if we're talking about properties, then our terminology is resistance, inductance, and capacitance. So resistance is a property wherein it opposes the flow of charge, whereas inductance is the property is to oppose any change in electrical current. Okay, once the magnetic field is built up, then it tries to oppose any change in electric current. Okay, instantaneous change, of course, because eventually it will die down or it will build up. As for capacitors, it resists any change in voltage, so somehow they are actually related to each other or similarly, but of course not really. Okay, anyway, continuing here, we have resistor. It dissipates energy in the form of heat, whereas inductor stores energy in a magnetic field, and for capacitor, it stores energy in an electric field. Right, so those are for passive and active elements. Okay, so now we'll move on to electrical sources, because recall here, here's our circuit elements. We have done discussing the passive elements, and now we'll be discussing these active elements. So for active elements, they're the ones producing the power in the circuits. So this can be voltage sources or current sources. Okay, so for voltage source, it says here a voltage source generates potential difference across a terminal. So an example is a battery. So it converts non-electric energy into electrical energy. Let's say right here in a battery, because of chemical reactions or chemical energy, then it is converted to electrical energy. Right, so we can produce this or we can light this bulb using these voltage sources. Okay, so when the terminals are connected in a closed path, then there's gonna be a flow of current. So that's why it's gonna be that's why this light bulb or this bulb will light up. So example of these voltage sources are actually a lot. Like this battery, it produces a DC voltage. Utility outlets produces AC voltage, and we have these USB ports in the computers or in our laptops, and also portable generators and power supply units. Now, I've mentioned about AC and DC supply. When I say DC, direct current, and we also have alternating current, or AC. This one is DC. So if we plot this graph, is direct current, it's actually a constant graph. So let's say here's a graph for our I and our in terms of time, and right here we have the voltage, and in terms of still I. So I in terms of time. And so the direct current, it has this graph. So it's just something like straight. It's constant all throughout, whereas the alternating current, it's a current that alternates. There are still many other waveforms, but this sinusoidal waveform is what we have here for these utility outlets, right? So those are voltage sources, portable generators. So when I say portable generators, it's just simply a generator. Let's say here's our generator. It resembles like an electric motor, except that the idea is different, because for the generator, then you have to input this shaft power. Let's say we need to rotate the shaft so that it can output electrical energy. Right, so mechanical energy, you input mechanical energy and the output is electrical energy. Whereas for electric motor, say here's electric motor, the input is electrical energy by, let's say, if there is a cord right here and we insert this cord into a utility outlet, maybe right here, then it produces mechanical power, right? So those that's the difference between the two. So portable generators is just basically a generator, and we have this, let's say, internal combustion engines, so it could be directly coupled or whatever design. So an internal combustion engine, we input fuel, and if it runs, then this shaft is going to rotate and we connect the shaft together, right? So those are portable generators or generator sets sometimes. And also we have these power supply units for electronics. So that's it. And for the current sources, it's a source of currents into the for the circuits. Like an example is this battery charger, right? So yes, this is our load, this is our voltage source, but after it uses its let's say its energy, then of course you need to charge it, right? So we charge it using a battery charger. Okay, so we need to input charges right here, currents. We need to input currents into this battery, right? So that's the current source.